Yeah, select the suitable field variable and the elements. What is the second step?
Discretization of the structure or the domain.
Discretization of the structure or the domain. And we have studied about discretization process also for different 5 steps while discretizing the continuum or a body. Okay. What else? What is the next step?
Selection of a proper interpolation model or displacement model.
Selection of proper interpolation model or displacement model. When we divide a body into smaller number of subdivisions which are called as elements, for each element we have to define a certain mathematical equation. So those are nothing but interpolation models or displacement models. So those can be of two forms, which is polynomial function or trigonometric functions. What is the next step?
Derivation of elements, stiffness matrices, and load vectors.
If we have to derive the, once we define the interpolation models, using those interpolation models, using potential energy approach or any other approach, we will derive the stiffness matrix for each element. Okay, stiffness matrix for an element for a given application. Okay, so that stiffness matrix can be used to solve problems on that particular application. Okay, then what is the next step once we do this?
Assembly of element
Yeah,
equations to obtain
assembly.
overall equilibrium equation.
So individual equations will be obtained, individual stiffness matrices will be obtained in the previous step. If we have two elements, we'll add those two elements and get the global equation. Okay, that global equation is nothing but equilibrium equation. After that, what is the next step?
Applying boundary conditions to obtain the unknown nodal
Yeah,
values.
so there will be constraints given to you, right? So those boundary conditions, those constraints are nothing but boundary conditions. So those boundary conditions will be applied and your matrix will reduce to some smaller size. Then you'll get some 2 cross 2 or 3 cross 3 matrix. Then you'll solve that equation to get the unknown field variables. Okay. So once you find out the unknown field variables, what is the last next step? What is the next?
Computation of elemental strains and
Yeah.
stresses.
Computation of element strains and stresses. Once we find the unknown field variables, using these unknown field variables, we find out what are your stresses and strains. Okay, using your stress strain relations or strain displacement relations. So there is one more here. You can just add it there itself, finding the reaction forces also. Okay, along with that. Okay. Now, what else you have studied? What else you have studied in the previous class? Discretization process. I've already told you there are 5 different steps in discretization process that you have studied. What else? Force distribution, right? What are the different forces which you come across over a body? So there are two types of forces. Which are those? Internal forces and external forces. What are internal forces? Internal forces get generated due to
External
internally
forces.
due to external forces. Okay, within the body. So what are the different external forces? You have studied 3 different types of external forces. For those 3 different types of external forces, you have written what are the equations for a whole volume. Okay, what are those forces? Body force, surface force, and concentrated load or point load. Okay, we have gone through that. Then we have written the equations. Okay, in general form, in matrix form. Next, we have gone through equilibrium equation. Okay, differential equation in 3D. So that is being shown to you on the slide here. Okay, now after that we have gone through what are the strain displacement relations and stress strain relations. Is it? Now in today's class we'll go through what is plane stress and plane strain. So after we go through plane stress and plane strain, we'll go through what are the phases in FEM. To know what are the phases in FEM, I'll just take a problem. Using that problem, I'll just solve that problem in the software and let you know what exactly are the phases in FEM. Okay. So what is plane stress? What is plane stress? What do you mean by plane stress and plane strain? Have you come across these two words earlier? Have you come across these two words earlier? Have you come across these two?
Yes, sir.
So can you tell what is plane stress and plane strain? Where you have come through this word plane stress and plane strain? What does this mean? Yeah. The clear definition of plane stress is been clearly written to you on your screen. The name itself tells plane stress. It means what? Stress in one direction will be negligible compared to the other two. Same with respect to plane strain as well. Okay, strain in one direction is negligible compared to the other two. We are only considering plane conditions. Okay, so a two-dimensional state of stress exists when the stress and the body forces are independent of the any one of the coordinates. Okay, either it may be x, y, or 0. If you consider x, whatever sigma x will be 0. Okay, whatever related to x will be equal to 0. If you consider z, so whatever related to z will be equal to 0. So example has been given to you. Such a state is described by body forces fx, fy, and stresses sigma x, sigma y, and tau x. Only these three stresses will come into picture. So here we are considering z is independent of coordinate axis. It means stresses in z directions are negligible compared to x and y. So if z is independent coordinate, then sigma z, that is your normal stress, and your shear stresses related to that direction will be equal to 0. Sigma z is equal to 0, then tau xz will be equal to 0, and tau yz also will be equal to 0. So this combination of stress components, which are functions of only x and y, are called as only functions of two coordinates. Either it may be x and y, yz, or xz, any two coordinates. Okay, so such problems are called as plane stress problems. Okay, so a definition is also given here: a thin planar body subjected to only in plane loading on its edge surface. For example, a plate with a hole. Okay, the loading is only in one direction, in plane. Okay, not in normal direction. Okay, so such problems are called as plane stress problems. What are the examples of plane stress problems where you can apply this plane stress condition? I've told you already, a plate with a hole, rectangular plate with a hole. There you can apply this plane stress condition. So I'll just take that example only and tell you what are the phases in FEM. I'll take a rectangular plate with a hole and pull it on both the sides. Okay, stresses will be there where the hole is. Okay, so I'll apply the plane stress condition for that. Okay, in the software, and explain you what are the phases in FEM. So other examples where you may apply plane stress conditions are, can you tell me other examples which are not there on the slide here? Can you tell me what are the other examples? A ring fitted on a shaft, washer. Any other examples where you can apply this? Where you can apply this? Yes? Can you tell me where you can apply this plane stress condition? So one coordinate will be independent of other two coordinates. Either it may be z, x, or y. Only there will be two components, either x, y, yz, or zx. There you can apply plane stress condition. A thin planar body. Can you tell me examples where you can find thin planar bodies? Wherever you find thin planar bodies, for those thin planar bodies you can apply plane stress condition, right? Is it right? Your blackboard is also a thin planar body, right? Is it right? Can you apply plane stress condition there? Yes? I hope you are noting down whatever is there on the screen here. Taken down? Now, for this plane stress condition, we'll write whatever the equations which we have gone through in the previous class: equilibrium equations, strain displacement relations, and stress strain relations. Okay, we'll apply plane stress condition to that, and we'll rewrite those equations now. So what is the condition here? Sigma z, tau xz, and tau yz will be equal to 0. So when these three are equal to 0, what will be these equations which you have gone through in the previous class? Okay, what these equations reduce to. So whenever in the exam plane stress and plane strain condition is asked, you have to define, you have to write this. Okay, give an example. Okay, draw a figure, okay, just a washer to which in plane loading is applied. You can see stress in these two, x and y, will be there, but stress when you compare to those two stresses, stress in z will be hardly negligible. Okay, there you can apply plane stress problems. Okay, you can draw this figure and you have to write all the governing equations. Okay, all the governing equations, equilibrium equations, then strain displacement relations and strain relations. So what, sigma z is 0, okay, tau xz is 0, tau yz is also 0. So when you apply that, your equilibrium equations only, there will be only two equilibrium equations. You cannot have third one because third one is related to z. All the three terms will be equal to 0. So these are the two equations which you get. Okay, dou sigma x by dou x plus dou tau xy upon dou y plus f of x equal to 0. Similarly with respect to y here. Okay, y here. So there will be no third component, that is sigma z. No sigma z. And similarly strain displacement relations, okay, only epsilon x and epsilon y will be there and gamma xy, no the third component. And stress strain relations, epsilon x, epsilon y, epsilon z will be there, strain will be there, not the stress. Remember this. Okay, strain component is there. Okay, so you can see here, to find out sigma epsilon z, in the previous class we have gone through. What is the equation of epsilon z? This is the equation. If this is equal to 0, what is the equation remaining now? Minus mu by E is a common, and that remaining term is your epsilon z. That's what, minus mu by E is a common and sigma x plus sigma y. The same thing, whatever is there above, just sigma z will be equal to 0. You should know those above equations. Okay, and next here gamma xy and gamma xz. Okay, so here shear stress, this two also will be equal to 0. Why these two are 0? Why these two are 0? Because tau yx, sorry, here tau xz and tau yz are equal to 0. If these are equal to 0, this also will be equal to 0, but not with respect to epsilon z, not normal stress. Okay, and remaining equations remain as it is, these two equations. And when this is written in matrix form, okay, epsilon x, epsilon y and epsilon z, this is what you get. Okay, epsilon x, epsilon y, gamma xy equal to 1 upon E, and this is the matrix, that is your strain constant matrix. Okay, D, and sigma x, sigma y and tau xy. Okay, so when you inverse it, this is strain. Now if I want only this stresses, sigma x, sigma y and sigma tau xy, you have to take this on the other side. You will find out to the what is the inverse of this matrix, and once you find out the inverse of a matrix, this is what you get. Okay, this is what you get. We are not worried about derivations here, how these expressions have come. Just you have to take this on the other side, it will be inverse 1 upon this matrix. When you take it above, it will be inverse. When you find out what is the inverse, this is what you get. Okay, so sigma x, sigma y, sigma tau xy equal to E upon 1 minus mu square, and this matrix 1 mu 0 mu 1 0 0 0 1 minus mu by 2, and this is your strains. Okay, so this is your plane stress conditions. Okay, so these are the equations which are applied to solve any plane stress problem. Okay, wherein sigma z will be equal to 0. It will not be sigma z all the times, so it might be sigma x also, sigma y also. Okay, any one coordinate, your values will be equal to 0, stress values will be equal to 0. Okay, you can take down these equations. I hope you are getting it. You should know only this much. Okay, where you can apply plane stress conditions. Okay, and these are the equations which you come across for plane stress conditions. Let me know once you take down. We'll move on to the next one. Any doubts in between you can ask. Okay, after today's class, in the next class we will go through potential energy approach. Okay, concept is small. Once we finish that concept, we'll solve problems on potential energy approach. Okay, in tomorrow's class. So after that we'll go to second half of the module. Okay, so which is interpolation models. So in interpolations models, you will learn what is simplex, complex and multiplex elements, how to write your polynomial functions. Okay, how to write the polynomial functions for a given element, you will know that. Then we'll derive the shape functions for simplex elements, simplex 1D, 2D and 3D simplex element. Taken down? I want the answer from you people. I cannot see the chat box. Taken down? Yes, are you people there? Just let me know. Hope I am audible correctly, right?
Yes, sir.
Okay, should I move on to the next one?
Yes, sir.
Okay. So now we have gone through what is plane stress conditions. Similarly, you have plane strain conditions wherein strain in one coordinate will be equal to 0. Okay, similar to plane stress, sigma z, tau xy, tau xz and tau yz were equal to 0. Here, epsilon z, gamma yz and gamma xz, normal strain, epsilon z, and your shear strains gamma yz and gamma xz will be equal to 0. Okay, if a long body of uniform cross section is subjected to, there it was thin body. Okay, there it was thin body. Here it will be a long body of uniform cross section is subjected to transverse loading as shown in the figure here. Okay, a loading along its length, a small thickness in the loaded area as shown. So it's not shown here. A small thickness here. Let me just indicate that here. Oh, sorry. Just wait a second. Yeah. If you consider a small region here, okay, this is your long slender body, okay, to which load is applied transversely. If you consider only small region, okay, in this small region, strain in x and y will be there, okay, not in z direction, okay, not in z direction. Got it, everyone? So if a long body of uniform cross section is subjected to transverse loading along its length, a small thickness in the loaded area, this in the loaded area, small thickness in the loaded area as shown is treated as plane strain problem. Only this portion is being treated as plane strain problem, okay, not the whole body. So for a longer body, in that only a small thickness, okay, infinitesimal thickness, that part is considered as plane strain problem. Okay, so wherever you have long bodies, if you take a smaller section of it, the strain in two directions will be there, and third direction it will be negligible. Okay, so two-dimensional state of stress exists when the strain are independent of one of the coordinates. Such a strain is described as plane strain problem. Okay, so only you have epsilon x, epsilon y, gamma xy. So z is independent, so epsilon z, gamma zx and gamma yz will be equal to 0. Okay, example where you can apply this. So analysis of dams. If you consider a dam, okay, there will be force, a water force which is applied onto the dam, right? If you consider only the small section of that dam, okay, strain in x and y will be there, okay, and strain in z direction will be hardly negligible. It will be independent of x and y coordinates. Okay, so cylinders, retaining walls, etc., there you can apply this plane stress problem. For smaller thin bodies you can apply plane stress conditions. For longer bodies you have to apply plane strain conditions. Okay, let just me move till I do it. Okay, you take down this. Okay, now as you have written the governing equations, equilibrium, stress strain relations and strain displacement relations for plane stress conditions, similarly we have to write what are the equations for plane strain conditions, what are the equations which are applied for plane strain conditions. You should know the above equations. Okay, then only you can write below equations. Okay, you should know all the three equations, equilibrium equations, all the strain displacement relations and all stress strain relations. Quickly you take down and let me know. I'll just show you the equations. Done? Should I show you the equations? Let me go to the let me go to the equations. So these are the governing equations, equilibrium equations. So here, I think so one more equation is missing here. Yes, here one more equation. Yeah, it is not missing. It is there. So this are the two equations similar to the previous one, and here epsilon z is not there. Okay, strain displacement relations. This is your strain displacement relation, and these are your stress strain relations. See here, you can see here. In the previous case, epsilon z was there. So here sigma z will be there, epsilon z will not be there. Okay, just take down these equations and just remember these equations. Don't think of how these equations have come. Okay, for that there is another subject. So these are the equations which are applied. Okay, which are applied for plane stress conditions and plane strain conditions. So epsilon z, gamma x, gamma yz and gamma xz are equal to 0. So once those are equal to 0, these are the remaining equations which you get. Okay. So epsilon x will be equal to 1 upon e sigma x minus mu sigma y plus sigma z. See here, sigma z is there. In the previous case, it was not there. Okay, here it will be there. Okay, so gamma xy. So other two are also 0 here. Sigma z will be there. Huh? Sigma z will be there. Mu sigma x plus sigma y. How this equation has come? I'll just tell you how this equation has come. From your last strain equation. Okay, from your last strain equations you will get this. So same equation, right? Epsilon z equal to 1 upon e sigma x. Okay, sorry, mu minus mu common, sigma x plus sigma y. Okay, plus sigma z will be there. If epsilon z is equal to 0, so what is only remaining now? 1 upon e minus mu sigma x plus sigma y plus sigma z. If you take this portion on the other side, this is what you get. Okay, I'll just show you from previous one. Where is that? Yeah, it's here. It's here. If this is equal to 0, if you rearrange it, so this is what you get. If you rearrange, this is what you get. And this is written in matrix form again here. Okay. There will be small variation in the matrix. So the above equations, previous one, they are applied for plane stress conditions. These are for plane strain conditions. Plane strain conditions. So this is about plane stress and plane strain. You should know where this plane stress applications, okay, and plane stress is applied and plane strain condition is applied. Okay, whenever you are doing analysis in the software, you have to specify which condition it is. Okay, you have to specify whether it is plane stress condition or plane strain condition. Okay. Finished? Taking down? Actual problems have not started yet, okay, with respect to FEM. They'll start from module 2. You have problems on module 1 also for 3 different approaches: potential energy approach, Rayleigh rates method, and Galerkin approach. Okay, we'll try to cover 2 approaches: potential energy approach and Rayleigh rates method. As of now, we'll first finish off potential energy approach. Okay, later on, at later stages, we'll come back to module 1 and then we'll go through what is a Rayleigh rates method. Finished? Whatever you are learning in this module 1 or all your basic introduction, okay, basic introduction. Should I move on to the next slide? Yes? Let me know. Let me move on to the next slide. Yeah. Phases of FEM. So there are 3 phases of FEM: preprocessor, solution, and postprocessor. As you have learned steps in FEM, general description of FEM, right? There are 7 steps. So those 7 steps you apply when you are solving any FEM problem manually. But when you are doing in any software, these are the 3 stages. Okay, preprocessor, these are 3 steps: preprocessor, solution, and postprocessor. So what you will be doing in preprocessor stage? Okay, all the basic necessities, everything will be doing it in preprocessor. Maximum out of 100%, 70%, 70 to 75% will be spending time on preprocessor only. Okay, and in solution, just you have to solve the problem. Okay, and in postprocessor, what we'll do is whatever results we want, we will just view those results and analyze the results. That is solution and postprocessor. What we'll do in preprocessor? Preprocessor will select what is the type of problem we are solving, whether it is a structural problem, whether it is a thermal problem, whether it is modal analysis problem. Okay, we'll select the type of problem here in preprocessor in the first step in preprocessor. Then we'll define what is the type of element. Okay, depending on the type of problem, we'll select what is the type of element. Okay, we'll select the type of element. We'll assign the type of element for a body. Then we'll define the material properties. Okay, we'll define the material properties. We'll model the component. Okay, we'll model the component. We'll apply the displacement boundary conditions and load boundary conditions. Okay, whatever the loads which are given, what are the constraints, all those will apply it here. Okay, all these steps will come in preprocessor. Okay, next, once we do all this, once we are Satisfied with all those things, we'll move on to solution. Okay, we'll solve it, your system will solve the problem. Then in post processor, if you want displacement, we'll view displacement. If you want stress, we'll view stress. If you want any plots, we'll view those plots. All those can be done. So these are nothing but phases in FEM. Let